Hi, and welcome back to Mechanics of Materials Part 2. So far in the course, we've completed the entire section on thin-walled pressure vessels and internal pressure, and we've now looked at the theory for torsional shearing stress and strain, and we've come up with the elastic torsion formula. And now we get into the exciting part where we start to solve some real-world examples for torsional problems. And so today is learning module 15, and the learning outcome is to solve for the maximum shear stress for an elastic torsion of a straight cylindrical shaft. And so here's an example. It's a steel bar, and it's fixed on the right-hand side over here, and we want to determine the maximum shear stress, and it has some torques applied to it. And so as a real-world example, this is just a small drive shaft, and it's a cylindrical shaft, and it could be subjected to different types of torques. And so the example that we're going to go through is very applicable to these kinds of situations. And so the first thing I have as a question for you is, how would you go about starting to determine the maximum shear stress in the structure? And what you should say is, well, we've developed a theory for that. We're going to use the elastic torsion formula. We're looking at elastic torsion here of straight cylindrical shafts. And so if you recall, that is tau. The shear stress is equal to the torque times rho, the radius out to the point that we're looking at the shear stress, divided by the polar moment of inertia. And so we know that the maximum shear stress is going to occur where rho is the maximum, and that's going to be at the outer surface of the cylindrical shaft. And so max tau occurs at outer surface. And so therefore, in this case, the diameter is 27.5, so rho would be half of that. So it's 27.5 divided by 2, or 13.75 millimeters. And that stays constant throughout the entire length of the shaft because it stays at the same diameter. And so J, therefore, is also, the polar moment of inertia is also constant throughout the shaft. So let's write that down. So J is constant throughout the length. And so my question to you is, we know rho now, we know J. Tau max is going to occur where T is max. And so let's write that down. Tau max occurs in our shaft somewhere along it, wherever the max T occurs, where T is max, the torque. And so how would I find out where T is max? So what we want to do now is we want to find which of these sections, from C to D or from B to C or from A to B, does the maximum torque occur. And so to do that, I'm going to go ahead and draw a free body diagram. Let's start with section CD. And so here's my shaft. I'm going to cut it at between C and D. I've got an applied torque of 4 times 10 to the 5th Newton millimeters. And then I have my resisting torque, T sub CD. To find out what T sub CD is, I'll sum moments in the Z direction, set it equal to 0. By the right-hand rule, 4 times 10 to the 5th is in the positive Z direction. So I've got 4 times 10 to the 5th. And then TCD is in the opposite direction. And I'm leaving units off because the units are shown on the diagram. So I've got minus TCD equals 0, or TCD equals 4 times 10 to the 5th Newton millimeters. Okay, now we want to do the same process for finding the torque in section from B to C, and I'd like you to do that on your own, and then let's come back and do it together. And so we have the FBD from B to C. Here's my shaft. I'll cut it between B and C. I've got the applied torque at the end, 4 times 10 to the 5th, and again I'm going to leave off units. Then I have in the opposite direction 2.5 times 10 to the 5th. And then I have my resisting torque inside that section when I cut it, which is TBC. Once again, I'm going to sum moments in the Z direction, set it equal to 0. So I have 4 times 10 to the 5th. And then the 2.5 by the right-hand rule is in the opposite direction, so it's going to be minus 2.5 times 10 to the 5th, and then minus TBC equals 0, or TBC equals 1.5 times 10 to the 5th Newton millimeters. And so now I've found the torque in section CD and in section BC. The last section we need to find is the torque in section from A to B, and I'd like you to go ahead and do that on your own and then come on back. And so to do the torque, or find the torque in section AB, we must first draw the free body diagram, and here I've drawn that free body diagram. I went ahead and sum moments in the Z direction, and I came up with TAB is equal to 5.25 times 10 to the 5th Newton millimeters. Remember, we found TCD to be 4 times 10 to the 5th Newton millimeters, and T from B to C to be 1.5 times 10 to the 5th Newton millimeters. And so the largest torque, where the largest shear stress is going to occur, is in section AB, because it has the largest magnitude. Okay, so here's our elastic. To wrap it up, we have our elastic torsion formula. We know what rho is. We're going to find J, which is constant throughout the cylinder. We have now found where the max T occurs, the torque occurs in section AB. So rho we found to be 13.75 millimeters. Here's the largest torque in section AB. This is a solid circular cross-section, so I want you to go ahead and calculate J on your own. Come on back. And when you calculate J, this is how we found the polar moment of inertia. And so we've got J equals pi over 2, and we're looking at the outer radius, so R is equal to 13.75, and we're going to raise that to the 4th power, and that ends up equaling 56,150 millimeters to the 4th. So I've got all my terms to find tau max now. So tau max equals max T, which we found was 5.25 times 10 to the 5th Newton millimeters. We have our rho at the outer surface, which is 13.75 millimeters. And we're going to divide that by J, which we found to be 56,150 millimeters to the 4th. And that gives me newtons, or 129 newtons per millimeter squared. Newtons per millimeter squared is the same as megapascals, so this is 129 megapascals. And that's our solution. So we have been able to find the maximum shear stress in this straight cylindrical shaft for elastic torsion. And we'll come back next time and we'll determine the angle of twist. And we'll see you then.